All right, today we're going to learn about angular and linear velocity in 6-2. Our objective is to find linear and angular velocity. All right, that's pretty simple. Okay, let's begin by talking about velocity in general. All right, you should know about velocity. Velocity is the change in distance over the change in time. All right, how something's distance is changing with respect to time, that's called velocity. All right, angular velocity is very similar, but instead of distance over time, it's the angular displacement, okay, over time. So instead of d over t, it's theta over t. All right, so just imagine a circle, and there's a particle traveling on the edge of a circle. All right, its angular velocity is the angle that it traveled in a given amount of time. So let's say that it traveled theta, or let's say it traveled 135 degrees, 135 degrees in 1 second. Okay, its angular velocity would be, actually, we have to convert 135 into radians. So in radians, 135 is 3 pi over 4. So we went 3 pi over 4 in 1 second. So the angular velocity would be 3 pi over 4. And that's radians per second. Okay. All right, so that's angular velocity. What about linear velocity? That's our third term that we need to know. Linear velocity is, let's go back to this idea of the particle. Okay, so you got a particle. It's traveling along the outside of this circle. Let's say this circle has radius r. Okay, radius r. And you want to know how fast is the particle moving? What is its velocity? What is its true linear velocity? Okay, well, in that case, we're actually talking about the arc length, because that's the distance it traveled. So it's still distance over time. It's distance over time. And the distance of the particle is actually equal to the arc length of the particle over time. Okay, and the arc length, we know that arc length is equal to the radians times the radius. Actually, this is radians, this is radius over time. So that's the formula. It's r times theta over t. So in this case, if r was 5, then we would have 5 times theta, which is 3 pi over 4, over t, also known as 15 pi over 4 over t. Great, so now we can calculate angular velocity and linear velocity. So that's our objective for today. Now let's actually practice it. Let's look at example 2. Example 2 says, determine the angular velocity if 7.3 revolutions are completed in 5 seconds. All right, so remember that the angular velocity is W equals theta over t. Theta is the angular displacement and t is time. Okay, so the angular displacement, we have 7.3 revolutions. All right, so how many radians is that? So we multiply 7.3 times 2 pi. 7.3 times 2 pi. And you get 45.867. And that was over 5 seconds, right? 5 seconds in the problem. So we want to divide that by 5. Divide by 5. And our answer is 9.17 3 radians per second. Cool, that's the angular velocity. All right, so a lot of times they'll actually give you revolutions and you have to convert it into radians. Let's go to example 3. Example 3 talks about a carousel All right, and this carousel is making 2 5/8 revolutions per minute. And we're trying to figure out what is the angular velocity, which is the theta over t, for this carousel. All right, so let's start off with what we know. All right, we're going to start off with, we know there's 2 5/8 revolutions in 1 minute. All right, so that's 2.625 revolutions per minute. We want to rewrite this in radians per second. So we're going to have to convert revolutions per minute into radians per second. All right, so there are, for every 1 revolution, there's 2 pi radians. Okay, and for every, so we cancel out, now we cancel out revolutions. We have radians up here. We want to get rid of minutes. We want to have seconds on the bottom, so you got to multiply by, there's 1 minute for every 60 seconds. Okay, so then cancel out minutes, and you're left with radians per second. Good. So now let's just do this calculation on our calculator. All right, so you got 2.625 over 60 times 2 pi, and we get 0.2748. Okay, 0.2748 or 2.275, I guess I could say. 0.275 radians per second. All right, so what we actually use here is called dimensional analysis. Okay, that's when you have an answer that's in the incorrect units. One thing you can do is you can always cancel out units until you get the correct answer. So we started with revolutions per minute, and then we knew that there was, well, this was just rewriting it. Then we knew that there was 2 pi radians for every 1 revolution. So we could cancel out revolutions with revolutions, and now we have radians, which is what we wanted. We had per minute down here, so we multiply by minute over seconds, and we have to do the correct ratio, and then we end up with seconds on the bottom. The key is you're actually, every single time you're multiplying by something, you're actually just multiplying by 1. You're multiplying by 1 because 2 pi radians is equal to 1 revolution, so this is just 1. And 1 minute is equal to 60 seconds, so it's basically just 1. But you're doing it in a clever way so as to change the units from something that you don't want, which is revolutions per minute, to something that you do want, radian per second. All right, so that's dimensional analysis. It's really a very important thing to know, both in math and in science. It'll be really helpful for you to master that
example
technique.
4.
Okay. All right, example 4 says, determine the linear velocity of a point rotating at an angular velocity of 17 pi radians per second at a distance of 5 centimeters from the center of a rotating object. Round to the nearest tenth. Okay, so first let's write down what is linear velocity. Linear velocity, you should know it as arc length over time. What's arc length? Arc length is the radians times the radius over time. Okay, so it's theta times r over t. Okay, and then in this problem they actually told us that the angular velocity, which is theta over t, is 17. So they actually gave us this part of it. All right, so they know that 17 pi over 1 second is your theta over t, and then all you have to do to find the linear velocity is multiply by the radius. So multiply by r, which is 5. All right, and then you multiply 5 times 17. All right, and that's 85 pi. And the units are no longer radians per second. It's actually just it's actually just equal to the centimeters. Okay, so it's just centimeters. Because remember that arc length is a unit of distance. All right, so 85 pi per second. So 85 pi centimeters per second. And we wanted, they told us in the problem to round it to the nearest tenth. So we got to do that. Let's go to our calculator and multiply 85 times pi. 85 times pi is 267 centimeters, or 0.0 centimeters per second. There we go. That's example 4. Okay, what about example 5? In example 5, we're supposed to once again look back to the beginning of the lesson. Okay, so you have a carousel. In this carousel, we know the angular velocity is 0.275. We actually just figured that out in example 3 is our angular velocity, which is theta over t. What is our linear velocity? Okay, and that's if r is 11 feet. Okay, so if it's 11 feet for the radius, what is our linear velocity going to be? Well, it's going to be the same as the problem that we just did. Linear velocity is theta times r over t. They just gave us theta over t is 0.275. So we got 0.275 times r is going to be our linear velocity. So we multiply 0.275 times the radius, which is 11. Okay, and 11 is equal, so it's 11 times this. And the units are in feet per second. Okay, so let's do that real quick. So 11 times 0.275. Alright, and then you get an answer. It's 3.025 feet per second. Alright. Then the problem also has a part B. It says there's a rider on the outer circle of a carousel. Now the outer circle of a carousel is 20 feet from the center. Okay, so instead r would be 20, and you do the same computation, 20 times 0.275, and you figure out the velocity is about 5.5 feet per second. Okay, so you could tell that if you're on the outside of the carousel, you're actually going a lot faster than on the inside. Let's take a look at example 6. In example 6, it says the tires on a race car have a diameter of 30 inches. If the tires are turning at a rate of 2,000 revolutions per minute, determine the car's race speed in miles per hour. Okay, up until this point, when we've talked about linear velocity, we've only talked about linear velocity as a particle traveling around a circle. But I want you to realize that that's actually equal to the distance traveled by the car. And to demonstrate that, I have a roll of tape. Okay, I have a roll of tape, and I'm going to unravel the tape. There we go. And I did one revolution. Okay, so I did one revolution of the tape. And let's see here. One revolution of a tape. And what is the distance that it traveled? It actually traveled exactly the circumference of the tape. Nice. So the distance traveled by the tape was equal to the circumference of the tape. So the velocity of the car. So we got that. So the velocity of the car is equal to the linear velocity of a point on the outside. So the velocity is equal to the linear velocity, which is equal to, well, we got to do the dimensional analysis here. So we got 2,000 revolutions per minute. That's the angular velocity times the actual radius, which is 30 inches. Actually, sorry, it's 15 inches because it's half of the diameter. Okay, and we want this in miles per hour. So it's in revolutions per minute times inches. We want this in miles per hour. Okay, so first thing we want to do is we want to convert to radians. Okay, so we got revolutions, let's convert to radians. There is, for every one revolution, there's 2 pi radians. Alright, so revolutions cancel out. Next, we have inches per minute as our units. We don't want inches per minute; we want miles per hour. So there's 12 inches in 1 foot. So basically, whatever's on top, I want to cancel it with the same thing on the bottom. So if I have inches up here, I want inches down here so I can cancel them. And I got to feet, and there's 5,280 feet and 1 mile. So my feet cancel. And now I just have miles per minute, but I don't want miles per minute, I want miles per hour. So to cancel out minutes, there's 60 minutes in 1 hour. Okay, so the minutes canceled. And now my final answer is going to be in miles per hour. So I just have to do the computation. Okay, so let's do that now. Computation is going to equal, all right, 2,000. I like to multiply everything on top first, times 15 times 2 pi times 1 times 1 times 60. Okay, enter. And then divided by the bottom, which is just 12 times 5,280. Enter. And you get 178.5 miles per hour. Neat. So now we know that this race car is going 178.5 miles per hour. Cool. And that pretty much ends the lesson. Now you know how to calculate race car speed and everything. So that's linear velocity, and you've also learned angular velocity today.